Hi everyone, and welcome to Eric's Electronics Workbench. So a while back I purchased this IFR model 2186 5 GHz programmable attenuator, and it's rated to adjust from 0 to 130 dB of reduction. Now I have a lot of these fixed attenuators, for example this one right here, this is a 6 dB attenuator. But I thought in some test setups it might be handy to have an adjustable attenuator where I could just dial in different values and not have to swap in and out all those fixed attenuators. So I was interested in this model when I saw it listed. The price was right, but it was advertised as untested and sold as is. So I kind of thought maybe it had a problem or an issue going on. Well, when I received it, of course I hooked it up and immediately found that it does in fact have a problem. So let me show you exactly what's going on and we'll get started with the repair. Alright, so let me show you what the problem is with the programmable attenuator. So this coax right here is connected to my RF signal generator, and the signal generator is set to 100 MHz at 0 dBm output. Now the frequency is not important for this test, just as long as it falls within the range of the attenuator. And this coax right here is connected to the spectrum analyzer's input right up here, and we'll just use the spectrum analyzer to monitor the RF signal level that's coming out of the attenuator. Now it's important to note that the attenuator is actually bidirectional, meaning that instead of the input being on this connector, it could have been on this connector, and then this becomes the output. So the attenuator is basically made of mechanical switches that are opening and closing, and they're selecting various resistance values that make up the attenuation factor. So because you have resistance, you have loss as heat within the attenuator. So as the RF signal is going through the attenuator, some drop or loss occurs inside the attenuator, and then the remaining signal comes out. So the attenuator has to dissipate that loss as heat. That's why there's a mention right here of 1 watt max, or maximum power that the attenuator can handle. So all attenuators have a maximum power handling ability. So I'm really hoping that this attenuator wasn't damaged by an excessive RF input level, because if it was, it may not be repairable, or at least not economically repairable. Maybe it would require a second unit to salvage the parts from, something like that. So we'll definitely find that out when we get inside of it and take things apart. So looking over on this side, on the spectrum analyzer over here, I have the center frequency set to 100 megahertz, so that just matches the signal generator's output. The span is 1 megahertz, and the reference level, or the top graticule, is 0 dBm. So what should happen if the attenuator is working correctly and it's set to 0 dB, that just passes straight through with no reduction, then the signal peak should go all the way up to 0 dBm. And there will just be a slight loss in the coax, but very, very minimal. All right, so let me reach around over here to the other side, and I'm going to switch on the attenuator. Like so some numbers come up there. I think that's just a software revision. And then it says 130 dB. So it always starts at the maximum attenuation level. So 130 dB is the maximum. And I'll turn on the signal generator over here, right there. So the signal generator is turned on, so we have a signal here, but there's nothing measurable coming out because 130 dB is just not something that can be read right now on the display over there. Okay, so let me go around over here, and I'm kind of working on both sides of the camera. I'm going to reach here and go to 0 dB right there. Okay, so we do have a signal back over on this side. So right here, we can see that there is a signal peak right there. So let me get a marker on that. A marker, and marker number 1 is on. Is it on? There it is. Okay. So what we need to do is put the marker on the peak. So do that. So the marker is that red line, but it's kind of obscured, but it's right in the middle right there. So you can see M1 right here, and it says minus 25.32 dBm, 100 megahertz. So it's on the 100 megahertz from the signal generator. But minus 25 is way too low. So because that's on 0 dBm, this actually should be all the way up here, very close to the 0 dBm level. So right away we can see there's a problem. So go back around on the other side here, and what I'm going to do is start increasing the attenuation level. So by pressing the up arrow right here, it'll step through some attenuation values. So if I go hit the button one time, it goes to 6 dB. And we can see there's some additional attenuation over there, but it's still not right. It's way too low. Go to 12. Now it's at 18. Now that's reading at minus 43 dBm, so it's way, way off. Minus 24, minus 30. Well, this is just at 30, but that's reading minus 31. So now it's suddenly closer. And that's what I found, is that right around this setting right here, right around 30 dB, suddenly the attenuation seems to work a little bit better. So if I go to 36, very close over there, now it's saying minus 37. This is 42. I don't know exactly why this jumps in the increments that it's doing. It seems to just be the way it's working. Maybe it was already set up that way or something. I haven't really messed with it all that much, but I just found that pressing that arrow just kind of step through some various values. You can type in any value that you want, actually. You don't have to go in these increments. But anyways, this is at 42, and that's showing 43 over there, very close. Go to 48, that's showing 50, 54, saying about 56 or so over there. The values get a little bit closer. This is at 60, minus 61. Go a couple more steps there. That's 72. Yeah, it's very close there. 73. That's 78, 80, but it's pretty much down in the noise. I don't think it's going to pick up anything beyond that. It's way down there. Let me go back to 0 again. Okay, so then it comes back up and it's, way off again, minus 25. So just for the sake of completeness, I'm going to turn off the signal generator and just remove this coax right here. And what I'm going to do is just connect these two coax cables together with an adapter. So this adapter right here is just an N adapter. So just connect this in here. So this adapter is just going to simulate what it should have been doing at the 0 dB setting of the attenuator. So I'll get this connected like so. Okay, so the coax is just passing straight through. And I'll turn the signal generator back on. Okay, so now we can see over here, the marker is reading minus 1.7 dBm, and that makes perfect sense. There's basically a loss of minus 1.7 dB of signal through the coax. That's perfectly normal. There's I would say 6, maybe 8 feet of coax total here. So perfectly normal, not a problem with that. So the attenuator has way too much loss and attenuation through it in many of the settings, and then it seems to improve as you get down, 30 and then even further beyond that. So let's open this up and take a look at the mechanical attenuators in here and see if we can figure out exactly why it's doing what we're seeing happen here. All right, so to open up the 2186 attenuator is straightforward. Just remove these two plastic pieces that are on the back panel, just a single screw holding each one in place. And with those removed, then this metal ring is able to be removed from the back panel. And then with that metal ring out of the way, the covers lift right off. So the top cover right there and the bottom cover right there. So now that we're inside the instrument, this is the top view, and you can see that's just the back side of the circuit board. Now I don't know if I need to remove the circuit board or not, because if we take a look at the other side of the instrument, just the bottom right here. So these are the two attenuators, so I think the problem is going to be inside those attenuators, not on that other circuit board. So there's a metal bracket across here, and then this metal piece right here that has other components that are also attached to it, but there's numerous screws that are going through these brackets and then going down into the attenuator. So I certainly need to remove that hardware, and then I'll have to see if maybe the other circuit board needs to be removed, or do the attenuators lift out this way. So I'll continue with that disassembly. So there's no need to remove the circuit board. Everything can be accessed from the bottom of the instrument just the way it's sitting here. So by removing that bracket and getting that panel moved out of the way gives access to these attenuators. And you can see with all that hardware removed now, the attenuators are loose. So this one moves like so. This one moves as well. So there's a rigid coax that joins the two attenuators together with an SMA connector on each end, so I'll remove that. And there's two ribbon cables, one attaches here and one over here. The ribbon cables are for controlling the switches that are inside the attenuators. So getting those unplugged, then these attenuators should lift right out. Now the RF connectors that pass through on the front panel are not actually attached to the panel. There's no hardware on that front panel. And you can see that panel right there with the toroid transformer and that little bridge rectifier right there. That's angled up. It's just being supported that way because the wires are rather short coming off of the transformer down to a terminal, and I didn't want to strain those wires. And I'm noticing a number of calibration seals that are in here that have never been broken, so it's nice no one's been in here to tamper with this. And the usual reminder, if you are working on an instrument like this, you're doing so at your own risk. Now I know there aren't high voltages in here, except this is AC line powered, so use care and be safe around the AC line voltages. Use an isolation transformer. So again, if you're following along, you're absolutely doing so at your own risk. So I'll get these attenuators removed and disassembled, and let's take a look inside. All right, so I have both attenuators disassembled. So you remove 4 screws and this top cover comes off that's over these solenoids, and there's 16 screws that hold this lower assembly with the resistive pads onto the main switch assembly. Now, all the hardware is metric, but these 16 screws on this portion are Allen head type screws, so you want to make sure you use the correct type of metric Allen key. Now, unfortunately, on the other attenuator, one of these screws right here, which is an M3 by 10 millimeter, was so incredibly tight that the head of the screw, the little Allen head, completely stripped out. So I struggled with that screw for quite some time trying to remove it. I was successful. I did finally get it out, and luckily there was no damage to the threads that are in this housing. So I just need to order up a small pack of these screws. I don't have any on hand, so that's a minor issue. But I have no idea why this one screw was so incredibly tight. All the other screws on this attenuator and the remainder on the other attenuator, came out very easily, but that one was just ridiculously tight. So with everything disassembled, I've inspected inside the attenuators, and everything looks okay. So I think the real issue is that the contacts in the switches were dirty. So electrically, all these resistive pads test out okay on both attenuators, which is very good news because it doesn't look like the attenuators were damaged from an overload. Now, the attenuators are each different, so if you put them side by side and you measure this resistive pad on this one and then you measure the other one in the same location, they may or may not be the same. But if you look at the structure of the resistive pad, they actually look different from each one. So the ones that look the same seem to measure the same, and then the ones that look different, of course, are measuring different. I don't have the actual resistive values. They might be printed on the other side of the pad. I'm not sure, and I don't want to remove them because these little clips are so delicate. But nonetheless, all the readings make sense. They're within reason. So for example, some of them are measuring as 50 ohms. I'm getting, an 80 ohm reading on some. I think one of them had a 100 ohm reading. Just numbers that seem to be reasonable. I'm not getting something that's, 50,000 ohms or some, ridiculously high values. And I'm getting the same readings on one like this one right here that has a certain look to the structure. When you look at that elsewhere, like right here, and then on the other one, you see it repeated again, they're measuring the same. Let me get you zoomed in a little bit closer, and you can see how these are actually made. So I'm going to move this out of the way here and just move this right up here. Very delicate. You have to be very careful with these. So there's gold-plated pads on each side, and that's where the switch makes contact. Okay, so each side, and then the resistive element is in the center. And electrically, you'll get a reading from one pad to the other, and you'll also get a reading from one pad to ground, which is the the case of the attenuator, and then from the other pad to ground as well. So it's basically like a T configuration. And also, if you take a note down in here, there's an RF absorbing material that's down in this slot to prevent standing waves and other undesirable effects. And then the general layout and design you can see is coaxial. So there's this slot that goes down the middle right here. And also on this piece right here, you can see this has this slot design. So they're keeping that coaxial 50 ohm impedance throughout the entire attenuator. So again, I think the pads on here just need to be cleaned, although they look to be okay, but I think they may have just tarnished very slightly. Gold is not completely immune from tarnishing. So the last thing that you want to do is go through and just spray this down with a contact cleaner. That would absolutely ruin the attenuator. You have to go through the very delicate cotton swab, soaked in a little bit of a contact cleaner. Just very carefully clean those pads. But again, it's a very delicate and fairly time-consuming process because you can't apply any force to these. They're very, very sensitive. So I'll definitely get started on that in just a moment. Now taking a look at the switch assembly right here. Oh, and one thing I want to add, that coax that links between the two attenuators, I tested that coax and it tests perfectly fine. So I was looking for any shorts or opens or anything on that, and I don't see any issues with that short section of rigid coax. So just taking a look at this switch assembly and how it actually functions. So you have these solenoids, and it looks to me like there's a center tap on the coil. So you have a portion of the coil, a center tap, and then another part of the coil winding. And these are activated with a pulse of voltage. So the pulse, and depending on how it's applied to the coil, causes the solenoid to move up or to move down. There's also a permanent magnet. So once these are energized and they move, they don't require power to hold them in position. So for example, if I move this one right here, you can see how that moves down, and then it stays in place. And if I turn this like so, you can see the one that I moved. See how those switch contacts have moved in the upwards position right there? Make sure this is in focus right there for you. So you can see how those are up right now. And then, for example, over here, these are still down. So when the switch contacts move in this up position like that, they make contact with, over here, the pads that are on the sides of these resistive elements, or the resistors that are in here. So that's how the switching action actually functions. So it's able to select which resistive pads are in use and which are bypassed. Now, going back over to this piece right here, when these switches are down, there's a switch contact on the bottom side. So when all of them are down, and I'll move this one back again just for clarity, like that. Okay, so when they're all in that position, see how that switch is retracted down again? This is a 0 dB setting, so you have the end connector right here, and the signal just passes straight through, and it's just a continuous continuity, I should say, between each switch. It's just going through all of these, all the way to this other end over here, and then on this other end, the final contact right there just makes contact right here on this little, oh, get that up there, this little piece right there, and that's the other side of the SMA connector right there, which is the output side. So now, keeping in mind that on the 0 dB setting, we had a very high amount of attenuation. So again, that tells me that very likely these switch contacts have just become dirty in here, and we're not making a good continuity through this, because in the 0 dB setting, it couldn't even pass a normal signal level. So what I'm going to need to do is very carefully clean all of these switch contacts. I don't see excessive wear, because when these strike the resistive pads, eventually they can wear out, but I don't see any evidence that that's happening. Everything looks okay mechanically. I don't see any problem. Nothing's binding. These all move the way that they're supposed to on both attenuators. So I'm very happy with the overall condition. I think it just needs some cleaning. So I'm going to get started with all of that, and then I'll reassemble them, and we'll continue with the testing and see if it's made an improvement, and hopefully it's working correctly. So I already mentioned that I took some resistance readings on the resistive pads in each attenuator, and they looked okay. What I actually hadn't measured yet was the path through the attenuator when it's in the 0 dB setting, meaning that all the switches are closed. And I thought, well, that would be a good idea to double check that, particularly because that's where one of the problems was showing up. It wasn't passing much of a signal even at 0 dB. So I have my ohm meter. If I touch the probes together, the reading just goes to very low value right there. So obviously that's what we should be seeing through the attenuator all the way to the end. It should basically be a direct continuity. So I'm going to probe into this end connector right into the center contact right there. And I'm just going to touch between each of the switches, okay? So start right here. Looks good, no problem there. Go to the next switch. No problems there. Go to the next switch right here. No problems there. Go to the next switch. No problems there. And the next switch. Yikes, that's a problem. So that's a very high value of resistance. It's kind of all over the place, and 150 k ohms. And then if you go all the way to this end tab right here, is very delicate. I have to be very careful touching this. And it's the same reading right there, of course. So I believe there's a problem right there. This switch, so if we go back one, see this goes up and over, so we go right here, we were looking okay. Yep, no problems there. So this switch right here, if I touch up on the top right here, well, it's a very high value up there. So this contact right there definitely has a problem, and it looks okay. It is making a good connection as far as physically touching, but there's something wrong, there must be tarnish or something on the surface right there that's preventing a good electrical connection. So I need to take very close attention to this area right here. So it looks to be where the problem is at. So I'll take a closer inspection on that and see if I can get that continuity to improve to the way that it's supposed to be. And I'll also take the same measurement on the other attenuator. I haven't done that yet, but I'll take the same readings. If I find anything going on that attenuator that seems really out of place, I'll definitely share that with you. All right, so after some very careful cleaning on the contacts, check out the result. So all the switches are in the closed position, so it's a 0 dB setting. So I'll come in here and probe into the end of this end connector again, go all the way to this last contact down here. Check it out. Very low resistance through all the switches. So that looks perfect, no problems. So I've actuated the switches a number of times, and they repeatedly close to that very low resistance value. So I think the issue is taken care of on this attenuator. So what I'm going to do is put everything back together on this attenuator, but not actually install it in the instrument. What I can do is actuate it manually. So with everything reassembled on it, put an RF signal in, take the output over to the spectrum analyzer, and then just like we were doing initially with the first test in the instrument, I can just actuate each of these solenoids, and this should step through the attenuation values. Now this won't go to the full attenuation value down to 130 dB because it needs the second attenuator to work with it as well. So this one will only go part way, but nonetheless we should see the steps, and it should be very specific and not have any variation. So I'll definitely do all that after this is assembled, and I'll show you those readings and confirm that this one is working correctly, and then if it is, we'll go on to the second attenuator. Alright, so all the switch contacts are cleaned in the first attenuator and it's reassembled, so let's test it and see if it's functioning correctly. So I have my RF signal generator set to 100 megahertz at 0 dBm output, and that's connected to this end connector on the side of the attenuator, and then the output is coming out of the SMA connector through this adapter into this coax and going into the spectrum analyzer. So I'll turn the signal generator on right there. And perfect, already there's a signal. So this is set to 0 dB, so it should just be passing the signal straight through right now with no attenuation. And we can see the peak is right at the top graticule, so that looks very good. The top graticule is 0 dBm. And as before, the center frequency is 100 megahertz, and then the span is 1 megahertz. All right, so let me put a marker on here. So marker, and we'll go marker to peak. Okay, so it's telling us that the marker right now on the peak of the signal is at minus 1.43 dBm. So that's basically just the loss that's in the coax right now, and there's a few feet of coax connecting everything, so that makes sense. So what I'll do is I'll go through and I'll manually activate, I'm just doing a calibration, I'll just manually activate these solenoids, and I'll step through and let's see what the attenuation values are, see if they make sense. So let me do this. I'm going to reach around over here, get my screwdriver, and I can move these solenoids right here. This, start with this one. All right, so there's the first one right there, and that says minus 21.32, so that loss that's in the cables, we can just basically subtract that from the value, and that would be about a 20 dB attenuation, so that makes sense. The next one right here, so that says minus 5.28, so that's about probably a 4 dB attenuator. Again, makes sense. Go to the next one, minus 21.3, so another 20 dB attenuator. Go to the next one right here. What do we have there? Minus 4.28, so that's probably a 3 dB attenuation. Just a smaller value on that one right there. And last one right here, minus 21.3, so another 20 dB attenuation. And that makes sense that there's actually several 20 dB attenuators, because when I was measuring the resistive pads in here, I remember seeing several of them reading the same. So it does make sense that several of these are the same value. Now if I activate several of them, so let's go back over here, this one's already activated, and I'll move this one right here. Now it says minus 41, so perfect. So they add up, so we have 20 and 20, of course 40. If I go to this one again here, there, and now it says minus 60, so perfect. So 20, 40, 60, exactly the way it's supposed to work. So this attenuator looks like it's functioning very well at this point. So I'll continue on with the second attenuator. I'll work on cleaning all the contacts, get it reassembled, and then we'll test it as well. All right, so I have all the contacts cleaned in the second attenuator, and it's completely reassembled except for this one screw where the Allen head's stripped out. So I have a small pack of screws that are on order, but they're not here yet. But not having this screw in place won't affect testing the attenuator whatsoever. Now for cleaning the contacts in these attenuators, I use this cleaner made by CRC, so it's intended for use on sensitive electronics, delicate components, and it's also plastic safe, which is very important. So CRC makes a cleaner that's intended for heavy duty use like on electric motors, and it's not plastic safe, so you'd never want to use something like that in this attenuator. It would completely ruin it. And you also don't want to use a contact cleaner that has a lubricant in it. I've mentioned using that type of a cleaner in things like potentiometers and other types of switches, but in a case like this, something with a lubricant would absolutely ruin this attenuator. So it needs to be a cleaner that dries to a completely clean and dry surface. So again, this CRC cleaner works very, very well, but you don't want to just go through hosing this down inside with the cleaner. What you do is just takes a very small amount, spray it onto the end of a Q-tip, go through and just very carefully wipe down the contacts, just kind of dab the cleaner on them, and also on the resistive pads, the gold-plated contacts on those as well. They're super delicate. You have to be very, very careful. So everything turned out very well. It's all cleaned up. So same test setup as before. I have the RF signal generator, 100 megahertz, 0 dBm. Signal is coming in right here. This is going out to the spectrum analyzer. So let's test it and see how it's functioning. So I'll turn the signal generator on right there, and perfect. We have a signal indication right there. So this is set to 0 dB, so all the solenoids are in that 0 dB setting. So let's see here, let's get the marker right here, marker to peak. Okay, so like before, we see it's minus 1.34, so we can basically subtract that value from the readings that we see and have an idea of what the attenuation values are as we go through here. So I mentioned that this attenuator appears to be different from the other one in the attenuation values. So as we go through, let's see how it compares. That other one, I recall, it had at least, it did have 3 of the 20 dB attenuation, one on the end, one in the middle, and one over here. So this one, I believe, is going to be different. All right, so let's go to the first one right here. And we see that says minus 21, so that would be a 20 dB attenuator. So that is the same. Click on the other attenuator as well. Go to this one right here. So minus 7.33. So that's probably a 6 dB attenuator. So the other attenuator did not have a 6 dB attenuation. That back up there. Let's see, this is minus 13 dB, so probably about a 12 dB attenuator. I know we didn't have that value on the other attenuator. Let's see, this one here, minus 6.48 it looks like, so probably about a 5 dB attenuator. So makes sense, no problems there. This is the last one right here. Another 20 dB attenuator, so this is minus 21.42. So like before, so if we take 2 of the attenuators and put them on at the same time, so this is already turned on. If I go to this one right here, perfect. It says minus 41, so the 20 and the 20, they add together. It's exactly the way they're supposed to. Now, it makes sense that there would actually be a total of 5 20 dB attenuators, because that would get you to 100 dB, and then this attenuator in total is supposed to go to 130, so you could add in some of the remainders and you know, you'd get to that total value. So it makes sense that they would need at least 5 of those 20 dB attenuators. So perfect. Looks like it's working very well. Put that back up there. Let's put this back up right there, and yep, back to the minus looks like 1.39. So perfect, no issues. Looks like it's ready to be reinstalled once the replacement screw arrives. All right, so this is the second attenuator that I was just testing with the spectrum analyzer. So if you're trying to verify if an attenuator is functioning correctly, you really do need to use an instrument like the spectrum analyzer or an RF power meter or even a network analyzer. Any of those instruments will help verify if the attenuator is functioning the way that it's expected to. But let's say you take some readings with an ohmmeter. What kind of measurements on the attenuator would make sense? What kind of readings could you expect? And what readings might be a little bit harder to interpret? So let's work through a few examples. Now, it's important to remember a couple things about an attenuator. First of all, it's intended to work in a 50 ohm environment. So we already saw the internal structure has that coaxial design for a 50 ohm impedance, and it's supposed to have a 50 ohm termination, and it's supposed to have a 50 ohm source. And you'll see in just a moment that that 50 ohm termination really does affect the readings that you'll get on the attenuator. And the attenuator doesn't function by just adding a high value of resistance, you know, through the attenuator from one connector to the other. So you might think of it more as the RF power is coming in, and then some of the power is being diverted to ground, and then some of the power is allowed to continue on. It's not just, again, a very high resistance that's being built up through the attenuator. It's really electrically different than that. And also, think of something like a volume control where you have that fixed resistance and then the movable wiper. Again, very, very different than what's going on in here. Okay, electrically, the resistance values in here don't work the way that something like a volume control works. All right, so let's take a few readings on here. So first of all, this is in the 0 dB setting. Yes, it is. These are all in the up position. So that means that the connection from this connector to this connector should just be straight through. So that's always a good measurement to make on an attenuator. So of course, if I just touch the probes together like so, you can see right there, very low resistance just through the test leads. So if I go over here to center contact on that end connector, and I'll just touch the center contact on this SMA connector right there. All right, so 0.29 ohms. So nothing wrong with that. So that verifies the connection through all the switches in here, and that's always a good measurement to make on an attenuator, just to verify that the switches are working correctly in that 0 dB setting. And also, you can take a measurement from the case of the attenuator to the center contact right here. And in the 0 dB setting, that should be an infinite or open circuit, and yes, it is. And it doesn't matter which way the polarity of the test probes are. You know, when you take these measurements, there's nothing in here that's polarity sensitive. And again, if I come over here to this end connector and touch the case, open circuit. So perfect, no problems there. So those are always good measurements to make. Now, let me turn on one of these. Let's go with this one right here. So now, if I go from the center contact of the SMA connector to the case, right there. So now we get 84 ohms, 84 and a half ohms. So you might be thinking, well, wait a minute, this is a 50 ohm, impedance this is supposed to work with. If you had, an RF device, an amplifier, a signal generator, something coming in, 84 ohms, it's not going to be happy with that impedance. There's something wrong. Well, no, not so fast. That is actually a normal reading. And if we come over to the other connector right here, touch to the case, and 84 and a half ohms, same value. So that's good to see. You do want to see that same reading on any of the attenuation settings. You're going to get the same resistance value that the way that I measured from this connector and then this connector. That is perfectly normal to see that. But the 84 ohm value, and that, again, higher than the 50 ohm value that you might expect to see, nothing wrong with that, and you'll see why in just a moment. So if we go through the attenuator now, all right, and I'll go to this center contact over here. Right there, I think that's touching. Don't want to short that out. Right there. It's not touching on that SMA connector. There it goes, right there. So 33 ohms through the attenuator. Now, not touching anything other than just adding this 50 ohm termination right here. So if I go from here's SMA connector, it has a 50 ohm resistor inside of it. So I touch right there, you can see 49.8 ohms, basically 50 ohms. So if I just install that right here. And this test, you could be doing this with a 50 ohm termination over here, wouldn't matter. So now, if I go over here to this, like this, my test leads are getting tangled up here. So now if I go to the center contact on this end connector and I touch to the case, 50 ohms, perfect. So now something like a signal generator or some other RF device that's connected to this would be very happy. It would see 50 ohms impedance and no problems whatsoever. So again, taking off this termination and not touching anything else, come back over here again to the case right here. 84 ohms. So that's why I was saying that 84 ohm value, nothing wrong with that, because when it's terminated with the correct impedance, then the measurements are correct and it would function the way that it's supposed to. So now, if I go over here, so for example, if I turn on this first one, remember on this one, this and this are both 20 dB attenuators. So if I activate this one and I take a reading, let's go from the center right here to the case. So that's 50 ohms, and we're not terminating it with anything. That just happens to be 50 ohms in this case. And just for completeness here, we can go through the attenuator as well, like so, and right here. So 80 ohms through the attenuator. And then if we go like that, and I will activate the other one. So now this 20 dB attenuator is activated. So if we go through the attenuator, all right, there it is, 80 ohms, no problems there, and center to case, we're back to our 50 ohms there. So in that case, you're able to compare, you know this is 20 dB, this is 20 dB, and they both measure the same with those resistance values, and you could say, well, you know, that makes sense, and it could maybe help you compare, maybe for troubleshooting purposes, if you were suspicious that one of those resistive pads had been damaged from excessive RF power. A reading like that could certainly be useful. And in fact, I did that when I was initially taking the measurements. Remember, I was saying that the structure of those resistive pads looked similar in several locations, and I was just comparing them to see if they were measuring the same. So before I reassemble the instrument, I just put the two attenuators side by side so that you have a better idea of how these work together inside the instrument to create all the attenuation values from 0 to 130 dB. So of course, when they're installed, these end connectors are poking through the front panel, and this SMA connector is joined to that SMA connector by that rigid coax you can see sitting right up there. So when I first received this instrument and I was, trying it out and kind of testing it, I noticed that you couldn't select 1 or 2 dB of reduction, but you could select from 3 all the way up to 130 dB. And if you try and select 1 or 2, it just jumps up to 3 dB. And of course, 0 dB is just, straight through the attenuators. We've already seen how that works. So after looking at these, it becomes obvious why you can't select 1 or 2 dB. And at first I didn't know if that was a problem or not, but again, looking at these, it's very obvious why, because the lowest attenuation setting is 3 dB right there. So then there's 4 dB, 5, 6 dB. Those are all individual pads that can be selected. But if you want 7 dB, of course, that would be selected by a 4 and a 3. 8 dB would be 5 and 3. 9 dB would be the 4 and the 5. 10 dB would be 4 and 6. And then the list just goes on, of course. Any value can be selected all the way from 3 dB to 130 dB by these 10 values right here. So pretty clever, and a little bit of a mathematical trick to get all the values out of these 10 numbers, but not have a 1 or a 2 dB. So I hope that just clarifies how these work together inside the instrument. So I know some of you might be wanting to look inside the instrument a little bit closer on that main circuit board. We didn't look at that earlier, so I'll reposition things a little bit here, and let's just take a quick look inside the instrument before I put it all back together. So let's take a look around inside the instrument. So off on the right-hand side of the screen is this toroid transformer and also a bridge rectifier that are mounted on that metal panel that fits in this area, so when everything's reassembled, they're just facing down towards the circuit board. This wiring here is joining the transformer and bridge rectifier through this connector down to the circuit board. It's a very large electrolytic capacitor here for power supply filtering, and several other electrolytic capacitors on the circuit board, probably for power supply filtering as well. So this ribbon cable controls one of the attenuators, and this ribbon cable is for controlling the other attenuator. And then this ribbon cable joins the main circuit board to the front panel circuit board. So on the front panel circuit board is the LCD display, the keypad, there's a display controller in this corner, and then in this corner there's a multi-turn trimmer potentiometer, and it appears to be the only adjustment inside the instrument. Now I'm not sure exactly what its purpose is. It might be for the display contrast. There's no display backlight, so I'm just guessing that maybe it has something to do with the display contrast. But I don't have a schematic for this instrument, so if anyone knows where you could download a schematic online, please leave that in the comments. I'd be very interested to obtain the schematic for this instrument. Now right here there's a movable jumper on the circuit board. It says PLD. Again, I'm not sure exactly what its function is, but you can see right here on the silk screen there's a little mark, and it looks like to be the normal position that they're indicating, but it could be moved to the second position. Now right here there's a metal tab, and it has these two devices on it. So that's a heat sink. It's just joined to the side of the chassis. So both of these are power FETs or MOSFETs. Each one has a gate, drain, and source marked by its leads. So usually if it's a voltage regulator, if it's a linear type regulator, they would often use a bipolar transistor, and sometimes also you would see integrated circuit type voltage regulators. So when you see a power FET or a MOSFET, usually it's for a switching regulator. But I don't see any inductors in here, so I don't think this is a switching regulator setup going on because, again, there's no inductor. This is a power resistor, another power resistor right here. So some type of control going on, power supply or something here, but I'm not sure exactly what. Kind of interesting. They also have what appears to be a temperature sensor on this heat sink, so they're very interested in monitoring its temperature, probably over temperature type protection. So when this runs, this doesn't seem to get particularly hot, so I'm not sure why they thought that this needed such a protection right here. There's no cooling fan in the instrument, but again, definitely we're interested in monitoring that temperature very closely there. So this chip right here with this label on it is the ROM or read-only memory, and it has a number that says 1.005, which is the firmware version, and that same number appears on the display momentarily when you power up the instrument. And this integrated circuit here says Zycore with a part number of X2816CP-20, and it's a 16K EEPROM. So EEPROM is an electrically erasable programmable read-only memory, so it would be holding parameters and other settings. These two integrated circuits here both have the same part number of M81C55-5, and they're both 2K static CMOS RAM chips. And this chip right here is the GPIB controller. It has a part number of D7210C. And then the main microprocessor is made by Philips, and it's this integrated circuit right here. And it has a part number of P80C652FBP. And this area right here, I'll just move the ribbon cable out of the way. There's a number of integrated circuits that all have the same part number right here. And they're made by Texas Instruments with a part number of DS3658N, and what those are is a quad high current driver. So they're able to control up to 70 volts or up to 600 milliamps and dissipate up to 2 watts. So it makes sense that they're all in this area right here because they're right next to these ribbon cables, and those are the integrated circuits that are driving the solenoids that are in the attenuators. All right, the 2186 attenuator is reassembled except for the top and bottom covers. So let's connect it to the spectrum analyzer and see if it's functioning correctly. All right, I have the attenuator connected to my HP8594E spectrum analyzer with a tracking generator. So let's take a closer look at the spectrum analyzer. All right, so the spectrum analyzer is sweeping from 9 kilohertz to 2.9 gigahertz, so that's its entire frequency range. And the tracking generator is active, and it's just following that sweep frequency. So this is going down to the attenuator, and then this is returning from the attenuator going back into the spectrum analyzer. Now this slight downward slope that you see on the spectrum analyzer's display is just the loss that's in the coax. That's to be expected. It's not a tremendous amount of loss, but as we get up here to 2.9 gigahertz, the coax does become more lossy. So I verified that that loss is not actually through the attenuator because I just connected the ends of the two coax cables together and it has this exact same slope. So we want to just see that slope remain the way that it is, but we want to step through some attenuation values and just make sure that it does drop down in value. So right now the top reference line is 0 dBm and the tracking generator's output is also 0 dBm. All right, so I'm going to go down here and I'm just going to keep the camera on the spectrum analyzer, but I'll tell you what the settings are on the attenuator. I'm not going to go through every possible combination. We'd be here all day doing that. So let's just start by going to say 5 dB right there. And yes, that looks good. No problem there. Drop down. Let's go to 10 dB. Looks good. No problem there. Let's try 20 dB. Perfect. No problems there. Let's try 30 dB. Perfect. No problem there. That flicker on the display is just because the line is going through that text over there. Let's say 45 dB. No problems there. That looks good. Say 50 dB. Very good. Now we're getting close to the noise floor, so we'll go to 60 dB. And yes, that looks reasonable, but that's pretty close to the noise floor right there. The spectrum analyzer, I think it goes down to about 70 dB, and I don't know if that's even going to be accurate. If I do that, there's 70 dB. Yeah, we're losing the accuracy there. That's into the noise. So now, to continue on, let's go to a different spectrum analyzer and see if we can verify that the attenuator steps down all the way to 130 dB. 130 dB is a lot of attenuation, so let's see what we can do to take that measurement. So to test the attenuator at its maximum attenuation setting of 130 dB requires that the RF signal be amplified first and then attenuated through the attenuator so that my spectrum analyzer can detect the signal. Otherwise, it's just completely buried down in the noise because 130 dB is a lot of attenuation. So starting with my RF signal generator, my Rohde & Schwarz SME06, it's set to 10 megahertz at minus 10 dBm. So 10 megahertz is just a nice, easy frequency to work with, no crazy losses in the coax cables and things like that. And the minus 10 dBm is because the signal is going over to drive my RF power amplifier, and it doesn't require a crazy huge signal to drive it. So minus 10 dBm is just what's needed. All right, let's take a look at the rest of the test setup. All right, so the minus 10 dBm signal from my RF signal generator is on this coax, and it's going into the power amplifier, which is an HP8347A. It's being amplified by plus 20 dBm. It's coming out right here on this coax, coming around to the attenuator, goes through the attenuator, comes out, and goes up to the spectrum analyzer. And you can see the attenuator is set to 130 dB. So let's take a look at the spectrum analyzer. All right, so the tremendously attenuated RF signal is connected to my HP3585A spectrum analyzer. So you can see the coax is connected right over here on this BNC connector. And on the spectrum analyzer's display, the center frequency is 10 megahertz. The span is just 200 hertz. The top graticule line is minus 100 dBm, and it's set to 10 dB per division. All right, so you can see the peak of the RF signal right there. And there's a little bright dot right there, which is the marker. And the marker is currently reading at minus 111. Now it says minus 110.8 dBm. So that's perfect. So remember that there's plus 20 dBm going into the attenuator, and then it's being attenuated by 130 dB. So it's offset by that plus 20. So again, if this is minus 100, then this is 110, 20, and 30, and it's offset by that 20 dBm. So perfect. The signal looks exactly the way it's supposed to, and the reading looks very, very good. And it fluctuates around just a little bit on the peak of the signal because it's such an incredibly small signal that any noises, anything around the coax can affect that signal and influence it. But again, it's looking very, very good at this point. So I think the attenuator is functioning the way that it's supposed to. Now if I go over here to the attenuator and I go from 130 to 120, go 120 dB right there. So now it should jump up. Yep, right there, no problem. So now this is up right at the minus 100 dBm, and because we have 120 dB of reduction, but there's an offset of 20 dBm, makes sense, sits right at minus 100. So it's perfect, no problems. So the repairs on the IFR 2186 attenuator are now complete. I'm definitely looking forward to having this on my workbench. I think it'll be handy for testing and troubleshooting purposes. So if you enjoyed this video, don't forget to give it a thumbs up. And if you're enjoying the videos on this channel, please remember to subscribe. There'll be many more videos coming up in the near future. Lots and lots of projects in the queue, and you won't want to miss any of them. All right, so as always, thank you for watching. Until next time, take care. Goodbye for now.